Hi. Welcome everyone. I am the current artist and curator for the Art of Science program at the Carl R. Woese Institute for Genomic Biology. So our interdisciplinary science institute not only supports incredible genomic research, but we also do a lot of work to communicate that research to the public. So we have a visitor today. Thank you. Will you introduce yourself and tell us a little bit about the kind of science that you do?
Hi, thank you very much, Julia. My name is Bruce Fouke. I'm an active faculty member at the Carl R. Woese Institute for Genomic Biology. I'm a geologist and a microbiologist, and I try to do a little bit of genomics. And I'm very interested in this concept of how life has evolved on planet Earth to deal with strong and sudden and very dramatic changes in the environment, things like temperature or chemistry or water. And so I study environments like coral reefs around the world. I look at hot springs in places like Yellowstone. We also have quite a bit of research on oil and gas fields around the world. And then we have a very strong active research program also on human kidney stones. So it's a very broad-based interdisciplinary mix of looking at how the growth of minerals has been harnessed by life to be successful on planet Earth.
Thank you. So today I'd like you to tell me a little bit about what is featured in the original image I used when I made the art piece out of your image.
So one of the absolute cornerstone pieces of our research is to use imaging, to use photography as a means to document what it is we're looking at. And again, we're focused on this idea of life and also the minerals and the rocks that life interacts with. And so we use photography as the sentinel cornerstone of all that research. Now, some of that photography, it's putting a camera in a backpack and skiing in the dead of winter into the middle of Yellowstone. And those involve a lot of photography in the field. But then equally important, we have close-up photography in the field. And then when we come back to the laboratory, we run experiments, and then we go down to the microscopy suite. That's part of the Institute for Genomic Biology. We call it the IGB core. And that's another form of photography when the cameras are mounted to very, very high definition and high resolution microscopes. And so we put this in a framework we call it powers of 10. And the powers of 10 means that you can consider whatever it is you're looking at relative to how large it is. And then you start off with something that's a certain size and you say, well, is something, what's 10 times larger, and then 100 times larger, and 1,000 times larger. And you work your way up to 1,000,000 times larger, and sometimes 1,000,000,000 times larger. So we do photography and imaging across this very broad range of powers of 10. The image that you're talking about, we call it sea glass, and it's actually something that that's actually quite an accurate way to describe it. It's just that the sea glass is 350 million years old. So we've been very concerned about this idea of oil and gas generation has really turned to this concept of fracking, which is to hydraulically fracture subsurface shales, which are organic matter rich, very dark, fine-grained rocks, to be able to break them and shatter them with water, and that's the hydraulic part. So hydraulic fracturing, and the code word is fracking. And this can have a lot of detrimental impacts on the environment, drinking water and the environment, the chemistries that are used and things like that. So we've been very interested in looking at ways that we can dramatically reduce that environmental impact. And so what we did was, the state of Illinois is actually in the middle of a large basin. It's like a big bowl. And we call that the Illinois Basin, and it's full of about 2 kilometers of limestones and sandstones. The majority of them were deposited in ancient oceans. And the Illinois Basin that we're sitting on top of now has got a lot of shale. Again, this dark fine-grained rock, and it's dark because it's full of oil, or very rich in organic matter. And so we went down to Southern Illinois with the Illinois State Geological Survey and the Prairie Research Institute on campus. And we were able to work with them to get a core. A core is when a well is built and they drill down into the ground upwards of 1.5 to sometimes 2 kilometers. And then they extract a column of rock out of that that we call a core. And then once that's removed, then they use that to help produce oil and gas and do fracking. And so we were able to get a piece of actual shale. It's called the New Albany Shale. It's Devonian in age. It's about 350 million years in age. And we were able to get a piece of that and then bring it back to the IGB, Institute for Genomic Biology. And then we cut it into very thin slices that you can actually shine light through. So it looks like rice paper. It's actually thinner than rice paper. We cut it to about 25 microns in thickness. And then we can actually shine different kinds of light through it and on it. And so the image that you're talking about was taken on a laser scanning microscope, a Zeiss laser scanning microscope, one of the many scopes that we have in the IGB core. And that technique allows us to take pictures at a scale of about 250 nanometers or even smaller, maybe down to 140 nanometers, right? 1 nanometer is 1/1000th of a meter. That's incredibly small, right? The thickness of a human hair would be dramatically thicker than this. So we can look in really, really fine resolution. And in an image, some of the beautiful kind of greenish colored particles in there are actually pieces of glass, but they're natural glass. It's actually called quartz, and it was quartz that was formed up in Alaska, Alaska, but also in Canada. And then it was transported down from the glaciers and then deposited in the southern Illinois basin. And so that quartz was moved by the ocean, sea glass, and then deposited on a deep ocean floor in southern Illinois. And those particles are actually real natural sea glass. And then in between that, you have some variety of colors that are caused by having fluorescent light hit the rock and then emit different wavelengths of light. And that's the oil. So the oil has its own color, and the rock particles, the quartz glass, has its own color. And that image is remarkable. No one's ever taken a picture at that resolution using those techniques before, using the laser scanning microscope and these types of ancient Devonian age shales, which are the target for oil and gas exploration. So that really sets the stage. The imaging for that is the fundamental cornerstone of us being able to run experiments to understand how can we decrease the impact of fracking on the environment. And we use the Illinois Basin as that exemplar environment in which we can run experiments both in the field and the laboratory to answer these questions.
That's wonderful. Thank you so much for telling us all about that.
Sure.
You answered my question about that specific image, but I was wondering if you wanted to add anything else about just how science imagery influences your work.
Yes. Science imagery is so critical, and I would say it's probably the most underrated yet incredibly important part of the scientific endeavor. There's many facets of doing cutting-edge science. One of them is to take measurements of, say, the chemistry, or measurements of the size, or measurements of the flow, or measurements of the temperature. And these are all incredibly powerful and important parts of building a scientific story of how nature has come about to have the processes that we depend on for our lifestyles. And but one of the things that oftentimes doesn't get quite as much recognition, I think, is building more, is the idea that imagery, being able to take a photograph of what you're looking at, it tells you so much. I think maybe one of the reasons why it gets sometimes overlooked is because it's so obvious, right? One of the questions, I really enjoy having a lot of graduate students and postdocs that I mentor at the IGB and the Illinois campus. And one of the things I always tell them is, if you want to ask a really good question at a meeting of very expert scientists on something, it's always a good question. Have you ever really looked carefully at what you're analyzing? And sometimes the people will say, absolutely, and here's the pictures. And other times people will say, we really haven't looked as much as we should, and we know we should, right? So imagery actually emerges for us across this Powers of 10 as one of the absolutely fundamental tools. And what we do is we'll take pictures of, I'll use Yellowstone as an example. The supervolcano of Yellowstone, the caldera, which is the middle bowl-shaped feature within the supervolcano of Yellowstone National Park. It's about 80 kilometers in diameter, 80 kilometers, right? And then some of the bison that are wandering around Yellowstone, and then standing in some of the hot springs we look at ancient life and mineral growth. You're talking about things that are on the scale of 1 or 2 or 3 meters in diameter. So we've gone from 80 kilometers all the way down to several meters. And then on the hoof of the bison, that's in the hot spring are some of the microbes we look at. And those microorganisms have, they're very small. On the average microbial cell is about 1 micron, 1/1,000,000th of a meter. So we go down to that. And then this new technology that we talked about for the oil and gas and the fracking, we use that also for our hot spring work with NASA to look for life on other planets. That goes down to 140 nanometers, and other techniques we use in the lab is even smaller. So basically, we go from 1/1,000,000th of a meter to 100 kilometers, right? So that's powers and powers and powers of 10. Each power of 10 is one step of saying something's 10 times larger, then 10 times again, then 10 times again, then 10 times again. And it's not uncommon for us to go through 10 or 15 powers of 10, going all the way from something enormous like planet Earth to something really tiny like a protein that's sitting inside the cell of a microorganism. So I guess the important point here is that imaging is so critical for us to do across that entire spectrum. And we even use imaging from satellites and spacecraft, not only of Earth, but of other planets as well. And so, and also, astronomy pictures, looking at the stars, we go all the way from that scale all the way down. But each one of those types of images at those different scales, they really tell us a piece of the story that we must have, because without imaging at each one of those steps, then you're never going to be able to have the full story come together, and you'll never understand really how nature has devised and crafted and evolved this incredible show of majesty and excitement that we call life on planet Earth.
Thank you so much. Yeah, I was so honored to work with your image. It's just so beautiful in its beginning form. So my main process while looking at it was to kind of highlight the fact that we're looking at it through these irises, through these camera lenses, and then to build a background of these ancient waters, because I just think it's really unbelievable and elemental to imagine the fact that like stone and water are so close to each other in our geology. And when we think about it in terms of human time, we think of those as being very different,
right,
things we interact with. But when you look at the core of what our Earth is made of, all of those things really, live together in a really interesting way.
And I think too, it's something that's so exciting about what you're saying is that, when you hold that kind of a shale in your hand, it's black, and it's the grains are tiny. So all you see is a kind of a big black blob, a big black blob is what I was trying to say. And it just looks like a big black rock without much information or nothing interesting. And then you start viewing it both in terms of the larger powers of 10, kind of where it was sitting in very deep water in the Illinois, and this is seawater in the Illinois basin, 350 million years ago. But then you dive into this scale of the hundreds of nanometer scale. And something that looks like an uninteresting black rock turns out to be full of this gorgeous aquamarine sea glass and all the different colors that you're talking about. And I think that, for me as a natural scientist, that's what's this constant sense of wonder, is that when we look closer and we look more deeply, and nature just keeps opening the book of history in front of us, what was there. And it's just so exciting, right? Because it's so unexpected. I think that's a big part of it, is that we as humans just don't expect something quite so beautiful to be hanging out that makes up a big black blob of rock that, we're not so interested in. So
wonderful. Thank you so much for joining us today. And I really appreciate all of your explanations and all of the work that you do. So glad to have you, Bruce. Thank you so much.
All right. Well, thank you for the invitation, and best of luck. Thank you so much. So, okay. Bye-bye.
Bye.